Welcome to Bedtime Astronomy. Explore the wonders of the cosmos with our soothing Bedtime Astronomy podcast. Each episode offers a gentle journey through the stars, planets, and beyond, perfect for unwinding after a long day. Let's travel through the mysteries of the universe as you drift off into a peaceful slumber under the night sky.
I want you to picture something for a second. Picture a single snowflake falling from the sky.
Okay.
You're bundled up, stick your tongue out, or, maybe you just catch it on a dark wool mitten so you can actually look at it closely. We all know that iconic, beautiful, six-sided crystal shape, right?
Yeah, the classic winter imagery.
Exactly. It looks incredibly intricate, almost magical. But there is a fundamental physical secret hiding inside that snowflake. At the very center of that beautiful, perfectly symmetrical crystal structure, there is a tiny microscopic piece of garbage.
Like a speck of dust or a tiny particle of soot or even a microscopic microbe swept up by the wind.
Right. And without that tiny piece of grit, the water vapor in those freezing winter clouds wouldn't have anything to cling to. It wouldn't have a starting point to freeze and actually build that beautiful ice crystal.
It needs an anchor.
Exactly. The water vapor would just stay as a supercooled gas, completely invisible, just endlessly floating around in the atmosphere. Every single snowflake requires that microscopic piece of debris to crystallize around. Now, I want you to take that idea, that concept of a tiny physical seed sparking the creation of something solid, and I want you to scale it up, like way up.
We're going big.
Past the clouds, past the atmosphere, all the way to an astronomical level. I want you to imagine the formation of moons, of massive asteroids, and, the very planet that you are standing on right now.
That imagery really brings us to one of the most profound mechanical mysteries in planetary science. When we look back about 4.5 billion years ago, our solar system started out as a wildly hot, violent, chaotic environment.
A completely hostile place.
Beyond hostile. It was essentially a massive swirling disk of gas and plasma surrounding a brand new, incredibly active young sun. But the core question that has, bothered scientists for decades is how did the very first solid objects physically condense out of that intense heat?
Right, because everything's melting.
Exactly. In an environment that extreme, surrounded by vaporized rock, how do you get the very first piece of solid material to just appear out of thin gas?
And today, we are going on a journey to answer that exact question. We are tracing the first solid matter in our solar system back to its absolute origins. We're going to uncover how ancient, long-dead stars provided the secret ingredients for the very ground we walk on.
It's a crazy story.
It really is. And incredibly, we are going to see how the mind-bending scientific tools used to discover this ancient stardust are, right now, unexpectedly pivoting to detect human bone diseases in medical clinics here on Earth.
Yeah, it is a remarkable chain of events connecting literally the oldest materials in the known universe to modern medical diagnostics. But to even begin to understand the dawn of the solar system, we have to acknowledge a major hurdle. We cannot rely on the rocks here on Earth to tell us the story of our origins.
So I'm going to push back on that for a second because it sounds, incredibly counterintuitive. If we live on Earth and we know the Earth was formed at the beginning of the solar system, why can't I just go into my backyard, dig a really deep hole, and look at the rocks at the bottom? Shouldn't the oldest rocks on Earth tell us how the Earth was made?
You would think so, right? But the Earth is a geologically alive planet.
Oh, like tectonics and stuff?
Exactly. We have plate tectonics, active volcanoes, constant erosion from wind and water, and subduction zones where the crust is just being dragged back down into the mantle. The Earth is essentially the ultimate geological recycling plant.
It just churns everything up.
Constantly, melting down old rocks and forging new ones. The rocks in your backyard or even the rocks at the bottom of the deepest mine have been melted, pressurized, and reformed countless times over the last 4.5 billion years. Their chemical memories have been completely wiped clean.
It's like trying to find the original tree in a piece of printer paper.
That is exactly it. So, if we want to understand the true infancy of our solar system, we have to look for cosmic fossils. We need materials that formed in that initial chaotic disk and have been locked in a deep freeze, completely unaltered, ever since. And the only way we get our hands on those is when they decide to fall from the sky.
Which brings us to a very specific, incredibly dramatic moment in history, early 1969. I want to set the scene for a moment. It is February 1969.
A big year for space.
Massive. We are just a few months away from Apollo 11. The entire world is completely obsessed with the space race. Laboratories across the globe have just spent millions of dollars upgrading their equipment, building pristine, clean rooms, and calibrating their instruments because they are anxiously waiting for Neil Armstrong and Buzz Aldrin to land on the moon and bring back the first ever pristine space rocks.
They were totally geared up.
Totally. But while the whole world is looking up at the moon waiting for summer, the universe decides to throw a massive delivery right at our front door in the middle of winter.
The arrival of the Allende meteorite.
Yes. It blazed through the Earth's atmosphere over the state of Chihuahua in Mexico. Eyewitness accounts describe a massive fireball lighting up the night sky, followed by sonic booms that shook the ground. As it slammed into the thicker parts of the atmosphere, it broke apart, scattering an unbelievable 2 tons. That's roughly 1.8 tons of rocky fragments across hundreds of square miles of the Mexican landscape.
The timing of the Allende fall is almost cinematic. I mean, you have the global scientific community fully mobilized. You have researchers who have spent years preparing to analyze extraterrestrial rocks, completely primed and ready to go.
Just waiting for something to test.
Right. And suddenly, 2 tons of the most pristine, ancient material anyone has ever seen just drops out of the sky. Local residents were picking up black, fusion-crusted stone from their fields and driveways. Within days, scientists were on the ground, gathering up these fragments and rushing them into the very labs that were waiting for Apollo.
We hear the term primitive meteorite thrown around to describe Allende, specifically a carbonaceous chondrite. Let's break down that jargon, because carbonaceous chondrite doesn't exactly roll off the tongue.
No, it really doesn't.
When I look at the physical descriptions, carbonaceous means it's rich in carbon and organic compounds, and chondrite refers to the fact that it's packed full of chondrules. These are tiny, round, previously molten droplets of rock that formed in space. Why is that specific combination the holy grail for cosmochemists?
Well, the presence of those features tells us we are looking at raw, unprocessed construction material. Think of a carbonaceous chondrite like a hard drive that was manufactured at the exact same time as the Earth.
Okay, I like this.
But instead of being used every day like Earth, where files are constantly being overwritten, the drive is reformatted, and the operating system is upgraded by tectonics and weather, this meteorite was unplugged at the factory, placed in a protective case, and left floating in the absolute deep freeze of space for 4.5 billion years.
Wow, so no geological tampering at all.
None. It has never been melted down by a planetary core. It has never been weathered by liquid water. It is the pristine raw material that existed before the planets even finished forming.
And because it was so massive, literally the largest primitive meteorite ever found on our planet, it gave scientists a staggering amount of material to work with. I mean, if a meteorite is only the size of a golf ball, researchers are terrified to destroy it for testing.
Exactly. You scrape off a millimeter and hope for the best.
Right. But with 2 tons of Allende, you had early pioneers in cosmochemistry at places like Caltech brilliant minds like Gerald Wasserberg and Dmitry Papanastasiou, who suddenly had access to this incredible, abundant resource. They could aggressively pick apart this rock, dissolve it, vaporize it, and measure it to figure out the exact baseline recipe that built our solar system.
And as those pioneers spent the 1970s analyzing these cosmic fossils, they started to build a consensus. They developed what became the standard model of our early solar system, often referred to as the homogeneous soup theory.
I always found this theory so elegantly simple. The assumption was that the early solar system, before anything solidified, was essentially a giant, well-mixed, homogeneous soup of hot gases and dust. And the logic behind this wasn't just a guess, it was based on hard data.
Right. The measurements backed it up.
When researchers analyzed Earth rocks, moon rocks, and bulk samples from meteorites like Allende, they found that chemically they were remarkably similar. We are talking about bulk isotopic analysis, showing almost identical signatures across the board.
We should define what we mean by isotopic analysis here, as it's really the foundation of everything that follows. So we all know the periodic table: carbon, oxygen, calcium, iron.
Yeah.
What defines an element is the number of protons in its nucleus. Every atom of calcium in the universe has exactly 20 protons.
That's the baseline rule.
Exactly. But atoms of the same element can have different numbers of neutrons. These variations are called isotopes. They act identically in terms of basic chemistry, but they have slightly different weights.
It's like having a fleet of identical cars coming out of a factory. They all have the same engine, the same paint job, the same interior. If you put them on a test track, they perform the exact same way chemically. But if you were to weigh them, you'd find a few of the cars have a trunk completely full of lead weights.
That's a great way to picture it.
Those heavier cars are the heavier isotopes. And what the early cosmochemists found was that if you count the ratio of normal cars to heavy cars on Earth, it was exactly the same ratio they were finding in the bulk meteorite samples.
And that isotopic consistency was interpreted as a cosmic fingerprint. It strongly implied that before the planets formed, the entire swirling disk of gas and dust around the early sun was perfectly blended together.
Like a smoothie.
Exactly like a smoothie. Every single planet, moon, and asteroid was baked from the exact same uniform batch of dough. The theory held that everything from previous star systems that contributed material to our nebula had been completely vaporized and mixed until all the original signatures were completely erased.
It makes complete sense. It's clean, it's tidy, and the math works out beautifully. But science rarely stays tidy for long.
No, it really doesn't.
The 1980s arrive, and researchers at the University of Chicago completely ruin this elegant theory with a massive, mind-bending plot twist.
Oh, yeah, they blew it wide open. A team led by Edward Anders at the University of Chicago was trying to track down the source of some very subtle, noble gas anomalies in these meteorites. And to find the source, they decided to essentially burn down the haystack to find the needle.
Literally.
Pretty much. They took pieces of primitive meteorites and subjected them to incredibly harsh chemical treatments. They dissolved the rocks in hydrofluoric acid, boiling away the silicates, the metals, the organics layer by layer, essentially destroying 99.99% of the meteorite.
Which sounds like absolute madness. You take an invaluable 4.5 billion-year-old space rock and you dissolve it in one of the most dangerous acids on Earth.
It takes some nerve for sure.
Seriously. But they were looking for whatever was tough enough to survive the acid bath. And what survived was absolutely shocking: nanodiamonds.
Microscopic diamonds, unimaginably small, like a single nanometer across, consisting of just a few thousand carbon atoms each.
That is tiny.
Beyond tiny. But it wasn't merely the presence of these diamonds that upended planetary science. It was the specific isotopic signature, the ratio of those cars with lead weights we talked about, locked inside these tiny crystals.
When the Chicago team measured the isotopes of the elements trapped inside these nanodiamonds, the ratios were completely off the charts. They didn't just differ slightly from the Earth or the Sun, they were wildly, astronomically different. They didn't match our cosmic fingerprint at all.
The anomalies were so extreme that they could not be explained by any chemical or physical process occurring within our solar nebula. The data forced planetary scientists to a profound conclusion.
This is the crazy part.
These nanodiamonds did not form in our solar system. They were presolar grains. They were actual physical remnants of an entirely different generation of stars. These were stars that had lived their entire life cycles, burned incredibly bright, and died in massive supernova explosions long before our own sun was even a glimmer in the cosmic eye.
I want to linger on this for a second because it is one of the coolest facts in all of science. You are in a laboratory holding a tiny dissolved residue from the Alende meteorite, and you are literally holding a piece of a ghost star.
It gives you chills.
It really does. You are holding solid material forged in the violent death of a sun that hasn't existed for over 5 billion years. These grains survived the blast of a supernova, floated through the freezing interstellar void for millions of years, and somehow got incorporated into the rock that eventually fell on Mexico.
And scientifically, what's fascinating here is it fundamentally shattered the homogeneous soup theory. It proved definitively that our early solar system was not just a perfectly uniform, vaporized mixture. It was spiked with solid, alien material that survived the formation of our solar system completely intact.
Like chocolate chips in the dough that didn't melt.
Exactly. It had unblended interlopers from older, dead solar systems mixed directly into the batter.
But as is always the case, answering one question creates a much more difficult mechanical puzzle. Finding the stardust was an incredible achievement, but where it was found inside the meteorites created a massive headache for the scientific community.
Yeah, the location was a real problem. Because following that initial discovery in the 80s, scientists isolated a variety of presolar grains, not just nanodiamonds, but silicon carbide, graphite, and other exotic minerals. However, there was a strict constraint on their location. They were exclusively found in the carbon-rich matrix of the primitive meteorites.
So let's visualize the structure of a meteorite to understand why that matters. Think of a primitive meteorite like a chunk of poorly mixed concrete. You have the cement part, the fine-grained, dark, powdery stuff that fills in the gaps and holds everything together. That is the matrix.
Right, the glue.
And then you have the gravel, the larger, distinct pebbles and droplets embedded in that cement. Those are the chondrules and the CAIs. The presolar stardust was only ever found in the cement. It was only in the matrix.
And the physical environment where that matrix formed is the crucial detail here. The carbon-rich matrix is known to have accreted under relatively cooler conditions in the outer, more distant regions of the early solar system disk, far away from the young sun.
Now, I have to play devil's advocate here. When we talk about the early solar system, we are talking about the vacuum of space. Space is famously brutally cold, near absolute zero. So why wouldn't the whole thing be a cosmic freezer? Why is the distance from the young sun the defining factor here?
It is a great question. Because while empty space is cold, an actively forming solar system is incredibly violent. The early solar nebula wasn't just a static cloud, it was an accretion disk. You have immense amounts of gas and dust collapsing inward under gravity.
Just piling up.
Exactly. And as all this material falls toward the center to build the sun, it bumps into itself. You have unimaginable friction, pressure, and magnetic forces generating intense heat. The inner part of this disk, where the terrestrial planets like Earth eventually formed, was an absolute inferno.
How hot are we talking?
We are talking about temperatures exceeding 1,500 degrees Celsius, hot enough to completely vaporize rock and metal into gas. Only the outer edges of the disk, out where Jupiter and comets eventually formed, remained cold enough to avoid this massive vaporization event.
So because the pre-solar grains, these tiny nanodiamonds and silicon carbides, are relatively delicate, it makes perfect logical sense that they were only found in the matrix. The outer edges of the early solar system acted like a deep freeze, preserving these fragile grains of alien dust from the violent friction of the inner disk.
Precisely. Yeah. And this logic dictated the scientific consensus for decades. The components of the meteorite that represent the gravel, the larger solid chunks that formed close to the young sun, were forged in that extreme, brutal heat.
The inner oven.
The cosmic oven, exactly.
Yeah.
The assumption was absolute. Any delicate presolar stardust that happened to drift inward from the cold outer regions into the inner solar system would have been completely obliterated. It would have been melted down, vaporized, and its unique isotopic signature totally erased by the intense heat.
It's basic intuition. It's like finding a piece of unburnt paper inside a solid block of glass that just came out of a 2,000-degree furnace. You don't expect the paper to survive the forging process. You expect it to turn to ash and become part of the glass.
Right, it shouldn't be there.
But this sets up a fascinating challenge. If everyone assumes the stardust is destroyed in the cosmic oven, what happens when a team finally gets the technology to look closely enough at the ashes?
Well, that brings us to the breakthrough research led by Francois Tissot and Ren Marquez at Caltech, published in Science Advances in July of 2026. They decided to challenge that exact assumption. They wanted to search for pre-solar grains in the absolute hottest, most heavily processed materials our solar system ever produced.
They targeted the ultimate gravel in our concrete analogy, something called CAIs, or calcium aluminum-rich inclusions. These are the bright white chunks you can see with your naked eye if you slice open the Allende meteorite.
Yeah, they really stand out.
They do. And from a chemical perspective, calcium and aluminum are refractory elements. That means they have incredibly high melting and boiling points. As the superheated gas of the inner solar system just barely began to cool down from its peak inferno, calcium and aluminum minerals were the very first things to condense back into solids. CAIs are literally the oldest forged rocks in the solar system.
And analyzing CAIs for pre-solar grains is a staggering technical challenge. I mean, you are looking for a microscopic isotopic anomaly, a few thousand atoms wide hidden inside a rock that was baked in a cosmic oven 4.5 billion years ago. To do this, Marquez had to invent entirely new methodologies. We are talking about pushing the absolute boundaries of mass spectrometry.
Let's talk about the mass spectrometer because it is the unsung hero of this entire story. The technology they were using in 2026 is vastly different from what they had in 1969. At a basic level, how does Marquez's specific tool actually find these anomalies?
Well, a mass spectrometer separates atoms by their weight, which allows us to count those different isotopes we talked about earlier. First, you take your microscopic sample of the CAI and you ionize it. You basically strip away electrons so the atoms carry an electrical charge.
Okay.
Then you accelerate these charged atoms through a vacuum tube at incredible speeds.
Like a particle accelerator on a table.
Exactly like that. And here's where the magic happens. As these atoms are flying down the tube, they pass through a powerful magnetic field. The magnet pushes on the charged atoms, forcing them to curve their flight path. This is the crucial sorting mechanism.
I love the visualization of this. It's like throwing a handful of ping pong balls and bowling balls around a sharp corner at 100 miles an hour.
That's a great analogy.
They're all moving at the same speed, but when they hit the curve, the lighter ping pong balls are going to get whipped around the corner tightly, while the heavier bowling balls have way too much momentum and are going to take the turn incredibly wide. The magnetic field is the curve, and the heavy isotopes, the atoms with the extra neutrons, are the bowling balls.
That is a perfect way to look at it. By placing highly sensitive detectors at different points along that curve, you can literally count how many ping pong ball isotopes land here and how many bowling ball isotopes land there. What Marquez did was refine the chemical extraction and the calibration of this machine to an unprecedented level of precision. They isolated tiny, specific fractions of the CAIs, dissolved them, and ran them through this magnetic curve.
And when they looked at where the atoms landed, they found the unburnt paper inside the glass. Marquez and his collaborators found undeniable, indisputable isotopic signatures of presolar stardust completely intact inside the hot-forged CAIs.
It totally defied decades of cosmochemical assumptions.
The survival of this stardust is just physically baffling. These grains survived the most violent, scorchingly hot environment imaginable. They were surrounded by vaporized rock, yet they didn't melt, they didn't vaporize. They held on to their alien isotopic signatures while sitting in the middle of a cosmic inferno. How is that physically possible?
The mechanism of their survival is still a subject of intense study. But the fact that they did survive isn't just a quirky anomaly. It actually provides the key to unlocking a massive mechanical problem that has bothered physicists modeling the early solar system for a long time. The survival of the stardust solves the riddle of how planets are built in the first place.
Okay, let's unpack the physics of that, because it goes back to why the homogeneous soup theory had a hidden, fatal flaw. If the inner solar system was a totally uniform mix of hot gas with absolutely no solid particles surviving, how do you get a rock to form?
Right, it comes down to the thermodynamics of nucleation. Nucleation is the physical process where a substance changes its phase, like a gas turning into a solid, or a liquid turning into a solid. For nucleation to occur, especially in a gas cloud that is cooling down, the molecules need a surface to grow on. They need a structural foundation.
Like a scaffold.
Yes. If there is no surface, no solid sea to anchor to, the gas can cool down significantly past its theoretical freezing point and still remain a gas.
This is the concept of supercooling. I always think about making rock candy as a kid to understand this.
Oh, that's a good one.
Right. You boil water on the stove and you dissolve a massive amount of sugar into it. Because the water is so hot, it can hold way more sugar than it normally would, creating a supersaturated liquid. But if you take that pot off the stove, pour it into a perfectly smooth, completely clean glass jar, and just let it sit there and cool, nothing really happens for a long time.
It just sits there as a liquid.
Exactly. The water cools down, but the sugar stays dissolved. It super cools. But the absolute second you drop a rough piece of string into that jar, or a wooden stick that has just one or two tiny sugar crystals already on it, bam. The sugar rapidly clashes out of the solution and crystallizes all over that surface. The string is the nucleation point. It provides the physical geometry for the crystal to start building itself.
That rock candy analogy translates perfectly to the cosmic scale. The early solar system was like that hot, supersaturated sugar water, but in a gaseous state. It was loaded with vaporized calcium and aluminum, and as the disk expanded and cooled, it was ready to condense into solid rock. But without a string, without a physical seed, the physics dictated a massive delay.
It would just stay as gas.
Right. Francois Tissot's work points out that without solid dust grains to disrupt that homogeneous mix of gases, the minerals would have taken far too long to condense.
But wait, how do we know they didn't just take a long time? The universe is incredibly old. Maybe the solar system just supercooled for a few million years until it finally forced itself to condense.
Well, we know the timeline was incredibly short because of isotopic decay clocks.
Yeah.
Cosmochemists can measure short-lived radioactive isotopes, like aluminum-26, which decays into magnesium-26 over a very specific rapid time frame. By looking at the ratios of these elements in the CAIs, we know with absolute certainty that these first rocks formed extremely quickly, within a few 100,000 years of the solar system's birth.
Which is a blink of an eye in cosmic terms.
Exactly. That timeline is physically impossible if the gas had to supercool and condense without a seed. The math simply doesn't work.
So the groundbreaking conclusion of the 2026 study is that the surviving presolar grains, the stardust that miraculously survived the cosmic oven, acted as the seeds for the CAIs. The ghosts of dead stars were the string in the rock candy jar.
They provided the essential nucleation points. Just like magma crystallizing deep in the Earth's crust or a snowflake forming around a speck of atmospheric dust, the highly refractory elements in the hot gas of the inner solar system grabbed onto the microscopic surfaces of these alien diamonds and silicon carbides. The rest of the CAI coalesced and grew around those crucial structural substrates.
It is genuinely awe-inspiring when you connect the dots.
Yeah.
It means these ancient dead stars didn't just passively float around our early solar system. Their pulverized corpses actively seeded the first rocks.
They were the catalyst.
Yes. They provided the exact physical geometry required for the brutally hot gases to grab onto and take solid form. Without those presolar grains surviving the inferno, the CAIs wouldn't have formed on the timeline they did. And if the CAIs don't form, the next stage of rocks doesn't form, the asteroids don't accrete, and ultimately you do not get the planet Earth.
It beautifully resolves the timeline constraint in cosmochemistry. What's fascinating here is the presolar grains weren't just anomalies hiding in the cold matrix. They were the fundamental architectural keystones operating in the hottest, earliest phases of our solar system's construction.
Figuring out the exact mechanics of how stars built the foundation of our planet is an incredible story of fundamental science. But the narrative takes a wild turn when we look at the aftermath of this discovery.
It really does.
Because the intensely precise mass spectrometers, the specific chemical extraction techniques that Ren Marquez invented to isolate calcium isotopes and find microscopic alien needles in a cosmic haystack, those exact tools are now being used to look inside our own bodies.
This transition from astrophysics to biomedicine highlights a deeply important, often misunderstood aspect of how scientific advancement actually functions in society.
It's the ultimate answer to the cynic's question. Someone might look at a Caltech study about a meteorite from 1969 and say, okay, a dying star made the rocks in my backyard. That's a cool trivia fact, but why should taxpayers fund this? Why does this matter to me right now on a Tuesday?
Right, the classic so what question.
Exactly. But the technological pivot here is direct, immediate, and potentially life-saving. The techniques designed to isolate and measure specific calcium isotopes in 4.5 billion-year-old space rocks are now being actively applied in clinical medical research.
Francois Tissot's lab is currently utilizing these precise mass spectrometry techniques on tiny samples of human blood and tissue. Their primary goal is to drastically improve the early detection of osteoporosis, a disease that affects millions of people globally by weakening bones and making them fragile.
I need you to connect the mechanics of this for me. How does a tool built to measure stardust in a meteorite actually detect bone density loss in human blood?
Well, to understand the connection, we have to look at the biology of how bones function. Your skeleton is not a static piece of scaffolding. It is living, dynamic tissue that is constantly being broken down and rebuilt in a process called bone remodeling.
It's always repairing itself.
Constantly. You have cells called osteoclasts that dissolve old bone tissue, releasing its minerals into your bloodstream. And you have cells called osteoblasts that pull minerals out of your blood to build new bone. In a healthy adult, these two processes are perfectly balanced.
And bone is primarily made of calcium.
Correct. And just like the stardust, the calcium in your body comes in different isotopes. You have lighter calcium isotopes like calcium-40 and heavier ones like calcium-44. When a disease like osteoporosis takes hold, the osteoclasts start destroying bone faster than the osteoblasts can rebuild it.
So you lose bone mass.
You lose bone mass. But here is the crucial biological mechanism. This process doesn't treat all isotopes equally.
Oh, this is where the physics meets the biology, right? The kinetic isotope effect.
Exactly. Because lighter isotopes have slightly less mass, they react a tiny bit faster in chemical bonds. When bones are rapidly broken down during osteoporosis, the body preferentially dumps lighter calcium isotopes into the bloodstream and urine.
So it subtly alters the overall chemical signature of your fluids, just like the anomalous nanodiamonds altered the signature of the meteorite.
Yes. When bone loss accelerates, the ratio of light to heavy calcium in your blood and urine changes in a very specific, measurable way. But the change is incredibly minute. Traditional medical tests, like a DEXA bone scan, rely on X-rays to look at the physical density of the bone. But by the time an X-ray shows that your bones have thinned out, significant irreversible damage has already occurred. You have already lost a massive amount of structural integrity.
You're just catching the aftermath.
Right. It's too late to prevent the initial loss.
But the mass spectrometer sitting in Tissett's lab wasn't built for X-rays. It was built to read the whisper of a ghost star hidden inside a rock that survived an inferno. It was built to separate the ping-pong balls from the bowling balls with a level of precision that traditional medical labs just don't possess.
And that is the breakthrough. By applying the cosmochemical extraction and measurement techniques to biological samples, the mass spectrometer can detect the minute isotopic shift in blood calcium long before a traditional bone density scan would ever register a problem.
That's incredible.
It allows doctors to see the process of bone loss happening in real time at the atomic level, rather than waiting years to see the results of the bone loss on an X-ray.
It is a testament to the unpredictable nature of discovery. You have scientists at Caltech trying to solve a purely theoretical physics problem about nucleation in the early solar system. And in the process of building the tool to solve it, they inadvertently create a diagnostic method that could potentially save millions of elderly people from severe, debilitating bone fractures.
This narrative strikes at the heart of one of the greatest debates in science policy, which is the tension between funding fundamental, curiosity-driven research versus applied research. Applied research is incredibly easy to justify to a funding board. You give a lab $10 million to find a more efficient way to store solar energy or to trial a specific drug for a specific cancer.
The goal is clear, the trajectory is linear, and the societal benefit is obvious and immediate. It's a straight line. We have problem X. Here is the money to find solution Y.
Exactly. But fundamental research like studying the isotopic signatures of primitive meteorites is driven purely by the desire to understand how the universe works at a base level.
Which can seem abstract to people.
It can. Critics often argue that it's an inefficient use of resources, that we shouldn't be funding astrophysics or space rock studies when we have pressing medical and environmental crises right here on Earth. But history consistently demonstrates that the most revolutionary, paradigm-shifting technologies almost always emerge from fundamental research.
Because it forces innovation.
Yes. This happens precisely because fundamental research forces scientists to invent entirely new tools and new ways of seeing the world just to answer their incredibly specific questions.
There's a quote that perfectly encapsulates this philosophy. François Tissot shared something his grandfather used to say, and it is the perfect distillation of why this matters. He said, "We didn't discover electricity by studying the candle."
It is a brilliant analogy. I mean, if a society only ever funds applied research to make a better candle, they might make great progress. They will find a slower burning wax. They will engineer a wick that produces less smoke. They might even figure out how to make it burn twice as bright.
Sure, you get a great candle.
But no matter how much money you pour into studying a candle, you will never ever invent a light bulb.
Because a light bulb requires a completely different fundamental understanding of reality. It requires you to stop looking at the wax and start asking completely unrelated abstract questions about electromagnetism, conductive filaments, and vacuums.
And in this case, we didn't invent a revolutionary new way to detect osteoporosis by exclusively studying bones. We found it by asking how a supernova builds a planet.
So what does this entire journey mean for you? It proves that human curiosity is this incredibly vast, interconnected web. By reaching for the oldest, furthest things in the known universe, by trying to understand the literal dust of dead stars, these scientists accidentally forged the key to better understanding the microscopic biology of our own bodies.
It's all connected.
The universe is fractal like that. When you look deep enough into the macrocosm, the tools you build will eventually reflect back to solve the microcosm.
It is a remarkable journey. We followed a single thread from a chaotic cloud of hot gas to a modern medical clinic, proving that knowledge is never truly isolated.
Let's just take a breath and recap the massive territory we've covered today because it's been an incredible ride. We started 4.5 billion years ago with a hot, homogeneous gas cloud that scientists long assumed was a perfectly blended, uniform soup.
The great cosmic smoothie.
Right. Then, the discovery of nanodiamonds, the anomalous remnants of ancient dead stars, completely shattered that theory, proving our origins were spiked with alien material. We watched a 2-ton time capsule called the Allende meteorite crash into Mexico in the winter of 1969, giving us the raw material to finally study our history.
We then explored the thermodynamic paradox of the cosmic oven. We uncovered how these delicate presolar grains didn't just miraculously survive the extreme heat of the inner solar system, but actually served as the crucial physical nucleation points The very seeds around which the first rocks, the CAIs, coalesced.
They were the microscopic grit at the center of the cosmic snowflake. And finally, we brought it all back down to Earth, showing how the unprecedented magnetic mass spectrometers built to measure that ancient stardust are, right now, measuring calcium isotopes to fight against bone disease. Unraveling the birth of the solar system is actively enhancing human health today.
It's a profound reminder of why we do science in the first place.
Absolutely. Now, I want to leave you with one final thought to chew on today. We've talked about how the very first rocks in our solar system, the foundation of the Earth itself, couldn't have taken solid form without the ashes of dead stars acting as their structural seeds. This means that the fundamental architecture of our world, the very ground you are walking on, the mountains, the continents, is literally built on the ghosts of previous universes.
It's a beautiful way to think about it.
Without the violent destruction of those ancient stars, our creation couldn't have happened the way it did. So as you go about your day today, I want you to look around, look at the mundane things, the everyday reality around you, and wonder what other invisible remnants of ancient history are silently, secretly holding your world together.
It is a profound perspective that makes you look at everything just a little bit differently.
Keep wondering, keep asking questions, and we'll catch you next time.